All right, today we're going to talk about something you've definitely felt, but you can't actually see. I'm talking about static electricity. You know, that sudden shock from a doorknob or the crackle of a sweater in the dark? We're going to unpack the incredible science that's hiding behind it all.
Think about it. That sharp little zap you get from a car door after sliding out. Or that crackling sound when you pull off a sweater. These aren't just random, weird things that happen. Nope. They are textbook examples of a fundamental force in physics called electrostatics. And that is exactly what we're going to dive into.
So here's the game plan. We'll start with that everyday spark we all know. Then we'll get into the two fundamental types of charge. After that, we're going to zoom way in to see the electron's role in all of this. We'll also figure out why some things conduct electricity and others, well, don't. And to wrap it all up, we'll even look at how you can detect this invisible force for yourself.
Okay, so let's get right to it. What's the real science behind these sparks and crackles?
This whole field of study is called electrostatics, and the key word here, you guessed it, is static. It just means not moving. So we're looking at electric charges that are just sitting there, building up on surfaces. They create all these fascinating effects before they get a chance to go anywhere.
Okay, now here's where it starts to get really interesting. Some of the earliest, simplest experiments revealed something absolutely crucial. It turns out there isn't just one kind of electric charge. There are actually two.
So picture this classic experiment. Scientists took two glass rods and rubbed them both with silk. Then they brought these charged rods close to each other. And what happened? They actually pushed each other away. This was a huge clue. It told them that both rods must have the same type of charge, which led to a big realization. Identical charges repel. So to double check, they tried it again, but this time with two plastic rods rubbed with cat's fur, and the result? You guessed it, the exact same thing. The plastic rods pushed each other away too. This just hammered home that first observation. Like charges definitely repel each other.
All right, this is where the puzzle really comes together. We know for sure that like charges push each other away. So what do you think is going to happen when we bring two different charged objects together? I'm talking about the charged glass rod and that charged plastic rod. What happens then?
They attract. It's the complete opposite. Instead of pushing away, they pull right towards each other. This was the aha moment. It proved brilliantly that the charge on the glass rod was totally different from the one on the plastic rod. And fun fact, it was actually Benjamin Franklin who came up with the names we still use for them, positive and negative.
And all of this leads us to probably the most fundamental rule in all of electrostatics. It's so simple, but it explains everything we've just seen. Like charges repel and unlike charges attract. That's it. If you remember one thing, make it that one. But okay, that raises a big question. Why do things get charged when you rub them together? What is actually happening on a level we can't see? To answer that, we have to go microscopic.
You know, it really all boils down to these tiny, tiny particles called electrons. See, everything is made of atoms, which have a positive center and these negative electrons buzzing around them. So when you rub two things together, you aren't creating charge out of thin air. No, you're just scraping electrons off one object and moving them to the other. The object that gets extra electrons becomes negatively charged, and the one that lost them, well, it's left with a positive charge. It's just a transfer.
So think back to that car door example. Why do you get a shock from the metal handle but not from, say, a wooden fence post? Well, it's because different materials handle this whole electron movement thing in very different ways. Basically, we can put materials into two big buckets. First, you've got your conductors. Think metals, our bodies, the earth. In these things, electrons are free to roam around. It's like a highway for them. Then you have insulators. This is stuff like glass, plastic, or wood. In these materials, the electrons are locked down tight. They don't move easily. And that's exactly why a plastic comb can hold a static charge, but a metal one just lets it flow away.
Okay, so we're talking about all this charge, but we have a problem. It's invisible. How in the world did early scientists even know it was there? How can we detect it? Well, they came up with a pretty clever little device to do just that. Check this out. This is a gold leaf electroscope. It might look kind of old-fashioned, but it's super effective. See that metal knob at the top? That connects to a metal rod that goes down into this glass case. And right at the bottom of that rod, you've got two super thin leaves of gold foil, just hanging there.
So how does this thing actually work? It's really smart. First, you take something that's charged and you touch it to that metal knob. Since the whole thing is a conductor, that charge immediately flows down the rod and spreads out over both of those gold leaves. Now think about it. Both leaves have the exact same charge. And what do we learn about like charges? That's right, they repel. So the leaves literally push away from each other. And the more they spread apart, the more charge there is. It's a simple but totally brilliant way to make the invisible visible.
All right, we have covered a ton of ground here, from sparks and shocks to electrons and gold leaves. So let's take a second and pull it all together with the key takeaways.
So here are the main things to lock in. First, there are two kinds of charge, positive and negative. Second, the golden rule, opposites attract and likes repel. Third, you can't create or destroy this charge, you're just moving electrons around. And finally, charge acts differently depending on its home. On a conductor, it moves freely. On an insulator, it stays put. So now we get that these charges push and pull on each other. But how much? How can we actually measure the strength of that force? Can we predict it? Well, that is the next big question. And answering it takes us right to the work of a physicist named Coulomb. But that's a story for another time. Thanks for joining me.